In this video, we will take a look at how we can improve data reliability using catalog-based dependency to express the relationship between your data transformation code, and time. For demos, we will use Trell, a data ops and automation platform that supports this approach to job design and automation. We start by reviewing some of the benefits of catalog-based dependency. Then I will present requirement for a simple data pipeline. We will examine a DAG-based solution and look at how data can become different from what you expect. Next, I will present a solution using catalog-based dependency. As we review the solution, I will connect various aspects back to the benefits mentioned earlier. I will also present a proof that catalog-based dependency mechanism guarantees planned behavior and results. I will show you the code for one of the jobs in the solution. Finally, I will demo the process of creating and running this pipeline. I will go through the failure scenario and solve it. So let's look at some of the benefits of catalog-based dependency. The primary benefit is that it is strict. You may wonder, in what sense? Well, when we design a data warehouse or data pipeline, we plan for a specific sequence of data transformations. Catalog-based dependency guarantees that during execution, the data it produces will follow this exact sequence, even in the presence of job failures or job delays. It achieves this by using the catalog to track the state of your data rigorously. That makes this a very robust approach and produces reliable data. Secondly, this dependency is implemented using only configuration and no code in almost all cases. You will see this in the example. The catalog in catalog-based dependency itself is special. Coupled with appropriate data organization and job design, it offers a number of features by itself. The most interesting feature is that it offers automatic time travel. Normally, we have to manually restore an older version of the data and run the appropriate jobs to fix things. Here, the jobs just know what to do and automatically time travel. That makes it easy to recover from failed or incorrect jobs as well as reproduce older runs. Catalog also permits perfectly isolated experiments and safe QA. I will also show how all data is lineage trackable and all job runs are auditable using original data. The catalog also makes it possible to spread out your pipeline or data warehouse across technologies while orchestrating and keeping track of data as it flows across the systems. So, the scenario we will examine is this. A company generates transactions during its operation. Transactions for a day are loaded into a BigQuery table at the end of the day. To analyze this, we need 30 days of this data maintained in a table. We also need a job to report summary statistics on this 30-day data. So in the DAG-based solution, we have sensor sense transaction day, which is responsible for detecting the presence of a specific BigQuery table. Once it is identified, it triggers append day, which will take this BigQuery table and load it into our 30-day table and also delete one day from the 30-day table to maintain 30 days of data. It then triggers report summary, which will generate the statistics and ship it off. So this looks pretty simple. So let's take a look at what happens during normal operation as well as during failures. What we see here is that for the first 2 days, the jobs run successfully and it leaves the data in the 30 days table in a valid state. Example, after the run on 12.3, max data is 12.2. When a job failure happens for append day, let's assume the best case scenario that the data is unchanged and still valid, but delayed. But when the jobs run for the next day on 12.6, if the failed job is not fixed by then, the data ends up having a missing day and is now only for 29 days. Here, the max day is 12.5, but is missing 12.4 because that failed, and the minimum has still advanced. So it's basically a 29-day data set. What should have happened is that 12.5 processing should be halted until 12.4 processing is fixed. This points to a fundamental problem. When using DAGs, you do not have a mechanism to get data state. Without the state of data, automation is unable to make correct decision regarding job execution. People have invented some ways to avoid this data problem, such as querying the data state using a sensor. But they become difficult to engineer as the number of jobs scale and the possible states that the data can take increase. The catalog based dependency mechanism offers a way to keep track of data state and define correct actions. Let's look at the solution starting from the sensor. The sensor here is different. It is a live process responsible for identifying transaction tables for any date. It polls a monitoring location for new tables. When one is sensed, the sensor will insert its path into the catalog tied to 6 dimensions. You may think of these dimensions as attributes. However, they are more appropriate as dimensions, as we do not allow duplicate entries with the same set of values. We will focus on the first two and explain two more later on. The first one is dataset class, which refers to the type of the dataset. This is a string that is a registered entity but can be automatically registered if missing. It has no code associated with it. This sensor, this specific sensor, gives value transactions to the paths it enters into the catalog. The second is instance timestamp. This is supposed to inform about the temporal properties of the data. The actual interpretation depends on the dataset class. In this case, a dataset with dataset class transactions and instance timestamp x must contain all the transactions for the day starting at x. No more, no less. The combination of dataset class and instance timestamp can be thought of as state, as it specifies what is present in the data subject to interpretation. We will use this terminology in the upcoming slides. This sensor does not do anything else except making entries into the catalog. It does not trigger any job. Before we get to jobs, let's also take a look at the 30-day table. The first decision we make regarding this table is that it is also entered into the catalog. The dataset class is transactions 30-day. When using catalog-based dependency, we must enter every data into the catalog under some classification. The second decision is to catalog it by day. The interpretation of instance timestamp is as follows. Transactions 30-day for instance timestamp x contains the transaction data for day starting at x and 29 days prior. Now, this may raise a question. How is this possible that the same table can be registered with three different combinations of instance timestamp when the table itself can only be in one of these states, most likely the most recent one? The answer is that we have separate paths for each state. Additionally, in general, data in any path when using catalog-based dependency is immutable. How this works is when we create 1130 data from 1129 data, we do not modify the 1129 table, but instead pick a new path for the 1130 data and directly write it completely into the new location. This is called copy on write. Each path contains 30 days of data. Furthermore, because data is immutable, the state of data does not change and it remains consistent with the state it is attached to in the catalog. This is what enables us to do time travel. By cataloging data with time and having the data be immutable means we can go back to any previous state of your data since the beginning of the data warehouse or pipeline. However, this is more than just having access to older data. This is having simultaneous access to older states along with the latest states. We have made historical data as accessible and actionable as current data. We will see that the jobs using catalog based dependency are able to take advantage of this difference. Let's take a look at job append day. But first, some nomenclature. Each possible run of a job is called a task. Each task has a scheduled instance timestamp. So, what does task of append day with scheduled instance timestamp x do? Well, given transactions for x and given transactions 30 day for x minus 1, it produces transactions 30 day for x. This is the catalog based dependency for this job. Now, this looks pretty simple, but is very powerful because it does four different things. The first thing is input selection. Now, in traditional DAGs, you have to write code to generate the paths where the inputs will be stored. Here, this is part of the rule itself. The paths can be supplied by the catalog. The second thing is input verification. For traditional DAGs, this involves verifying that each input path has data and that the data is in a usable state. This can be hard and is sometimes skipped, leading to data inconsistencies. In our case, our data has only paths containing data in valid states. The input verification only involves making sure that entries exist in the catalog. There is no need to check the paths themselves. The third one is output selection. This is also clearly part of the rule. A clean path will be provided by the catalog. The last one is scheduling. So, when should this task run? How do we pick a time? In other systems, we pick a time when the input data will be ready. In such cases, we are relying on clock time to make assumptions about data state. This can cause data inconsistencies. When using catalog-based dependency, we have clear access to state and there is no need to pick a time for scheduling the job. If the requirements are met, that is, in this case, if both the required entries are present, the task can simply be executed ASAP. Furthermore, this rule is achieved using configuration, not code. This avoids a large source of bugs and saves you time developing and testing automation code. Next, let us see how catalog-based dependency does state management and makes sure your data is valid. I will prove that the catalog in the future will consist of only data in valid states. Let's do an informal proof by induction. Let's assume that currently in the catalog, we only have a set of valid states. We have to prove that data remains consistent in three cases. The first one is jobs are successful and correct. Two, jobs failed. And three, jobs failed but were fixed. We will also explain what to do when jobs are successful but are incorrect, which means that your code has some bugs in it that doesn't cause it to fail. So let's get started on the proof. So the rule configuration of append day define tasks of this job to map from valid states to valid states. Now, if the inputs are valid, and they are, and task is successful and correct, then the output is also valid. It will be added to the catalog after completion automatically. So the first case is correct. If the jobs are correct and don't fail, catalog consists of valid states with no manual intervention. What if a job fails and produces data with invalid state? For example, append date 12.4 fails. Normally it will have to be fixed manually. But thanks to immutability, there's no need to fix the broken 12.4 30-day data. We don't even need to know what is the invalid state. The previous valid state 12.3 already exists in the catalog separately. The invalid data can just be ignored and it automatically is. Let me repeat, automatically ignored. In the absence of 30-day 12.4 state in the catalog, transactions 12.5 cannot be processed. Neither can reporting. So no new states are created, preventing invalid states. So this covers the second case. If the jobs do fail, catalog still consists of only valid states with no manual intervention. Now let's take a look at the third case. When you finally fix and rerun append date 12.4, everything catches up as fast as possible. How do we know that this will produce the correct results now that they are delayed? So, how this is achieved is in catalog based dependency, we make sure that jobs do not modify inputs. They only write outputs and do not access any other data. They are pure jobs. This paired with immutable datasets ensure that results do not change based on time and other context. This is called execution time invariance. So by induction, the catalog will consist of valid states only with no manual intervention, as we have covered all the three cases that is explained. The key assumption here is that a task must fail if it did not produce data in a valid state, and we must try our best to build jobs that follow this property. However, in practice, mistakes can happen. A job can produce invalid data while successful. For example, you forgot to D2 before a join, and now the rows are 10 times what it's supposed to be. You may also later decide that some parameters should have been different. Both of these put you in the same situation. So we have to consider this case. Now, obviously, this requires some manual intervention, but how do we fix it? So, for this, we start by deleting all the invalid datasets and their creation tasks. There is no need to deal with anything else, such as manually rolling back datasets due to the equal status of historic states in the catalog. The second step is we simply ask the system to resume regular operations and it will automatically produce the correct data again using the newly fixed code. So, if the job is successful and not correct, with a simple manual intervention, we can restore the catalog to valid states only. In conclusion, catalog based dependency offers highly automated data transformations that offer high quality data with minimal manual interventions. Having looked at all this, let's make a few observations. We can track the lineage of a dataset by going to the task that created it. This is possible in trial. We can keep trialing backwards through task executions indefinitely. Secondly, we can audit results of jobs by looking at the exact inputs used in the task. Due to immutability and copy on write, the older data is not deleted unless explicitly requested. The third one is that the catalog based dependency actually follows a familiar abstraction, and it's that of spreadsheets. For example, if rows corresponded to dates and columns corresponded to dataset classes, then the process of architecting a set of jobs to build some dataset is same as figuring out how to add new columns to a spreadsheet. This gives me confidence that you will find it easy to design jobs based on catalog based dependency. Let's examine two of the dimensions we have to provide for a path. The first is a label. It corresponds to the environment, such as prod or QA. Now, this is not a real entity, just a string associated with the dataset. You can make up labels as needed. Jobs specify labels for inputs and outputs. If you want to run an experiment, all you have to do is register a new job with branch code and a different label. Now, you can mix and match labels for inputs as long as output labels are not in production. This gives you tremendous safety when you run this parallel pipeline. The second one is repository. This corresponds to a root location where the data is stored. Now, this one is a registered entity and it is tied to a technology plugin as well as path configuration. Typical examples are a repository for a data warehouse, and a repository for the data lake, and this allows the catalog to track data in multiple locations. Jobs also specify a repository for each input and output. This makes sure that a BigQuery job is not given an S3 path. The last one is version. This is not a dimension that you actually provide, but it is determined by the platform. This is read only for the user and is primarily used to track updates. Version control exists because of the six dimensional space. If you insert a path to the catalog with a combination of attributes that already exist in the catalog, the new path suppresses the old path. Only one can exist. The newer path gets a higher version number. If two datasets have same dimensions, and this is an extra capability that is made possible by careful design of how the version works. If two datasets have same dimensions, including version, and differ only in repository, then there is a reasonable guarantee that they store the same data. I will not go into how that exactly works, but that's for another video. So before we get to the demo, let's take a look at what append the job actually looks like. It consists of two parts, the registration file and the code. So in the registration file, we start with the, the name as well as a job description. Then we have the repository map. This is used to specify the, the repository for the inputs. So here is it, they are both from BQ. Now this is the scheduler configuration. Like I said, this is pluggable code, and the plugin that we are using is called periodic, and everything else that follows is some configuration for the plugin. Now, again, I will not go into, and this is where we specify the label that we are using. I will not go into more detail, but in another video, I'll go over the various plugins and their parameterizations and the patterns that they implement. Here is where we select the output. And what we're basically saying is that the output is transactions 30-day, and all the other dimensions it will inherit from the schedule. Um, and here is where we download the source code. And this is the last thing. This is the execution profile. The execution profile helps your jobs code and can take care of common tasks such as one, creating a unique execution folder, checking out your code, input dataset read locking and output dataset creation and write locking, providing detailed information regarding the task to your code, resource allocation and deallocation, as well as timeout and return code. So it's a heavyweight plugin that helps you run any type of job and has vast freedom from the platform, the Trell platform, to support any kind of technology. So mostly as a result of the uh, capabilities offered by the execution profile, and also partly because of the capabilities provided by the scheduling system, the code for append is actually very small. In fact, smaller than the registration file. Given the fact that it is clearly told where the paths are for the inputs and where the path is for the output, as well as the details of the task itself, all that is really required to do is parameterize a SQL with the input paths as well as the instance timestamp, and save the results into the output path. There is a minor SDK use that wraps around credentials management as well as BigQuery API access. So next, let's take a look at the demo. For this demo, we use Trell, a data ops and automation platform that supports catalog-based dependency. We are starting with a clean instance of Trell with just the required credentials and repository. As we can see, there are no jobs or tasks or datasets or sensors in the system. So we'll start by first adding the sensor. For this, we have to create a registration file, and then we register it and we enable the sensor. So two commands, one to register and one to enable it. So let's get back and take a look at what's going on. Sensor is running, and when we look at the data sets, we see that transactions have started populating, and we have four transactions, four entries corresponding to four different tables that I had prepared. Okay, so For transactions 30 day, I have another table prepared, and there is no need for a sensor. I'm just going to enter that manually into the catalog. So this is the path for the table, and to enter it, I have the all the dimensions that are required to enter correctly. Okay, that is done. We can see it in the data sets here, and everything is good. Next, we need to create our jobs. So the process is, again, create the registration file and run the registration commands. So we have two jobs. So the second one is report summary, and we are going to register that as well. Okay, so now let's take a look at running it. So this is the command to run. Um, we're going to try and to run for 12.1, which it should refuse to do because it doesn't have the data to run for 12.1, because that requires the transactions 30 day for um, 11:30, which doesn't exist. So that's exactly what we see. So let's try running for 12.2, which it should be able to do. Great. So next, let's try running it for 12.3 using the scheduler. The scheduler requires two commands. One is to enable the scheduler, and the second one is to trigger the scheduler. I'm going to enable this scheduler for the report summary as well. And then let's trigger the scheduler for append day. And while we're at it, let's trigger the scheduler for report summary as well. Okay, so now let's go back. Now all the jobs are running. So we have two jobs, and we will look at the tasks. What we see is it ran for, let's see. So we have append day for 12.2, append day for 12.3, and report summary for 12.1, 12.2, and 12.3. All these reports have been sent out, and two append days run, but this append day failed for 12.4. That's because I created the table incorrectly, intentionally, so that the columns don't match up. So as you can see, no report for 12.4 has gone out. Even though, and append day for 12.5 has not run as well, even though it can run that because the transactions exist for 12.5, but because the transactions 30 day does not exist, it is unable to do so. Transactions 30 days stop at 12.3. So how do we fix this data warehouse situation where it's no longer making progress? So for that, we have to have the fixed data. So the fixed data is stored here, which we now register into the catalog with the same dimensions as the broken data, which will suppress the broken data and replace it. Okay. So if you go back to the data sets again, look at transactions, we see that the one for 12.4 has changed into the newer one. Now we'll use the UI for this. We go to our tasks, we look at the failed one, and we just say, I want to execute this again. We submit it. And at this point, if you look at the tasks, 12.4 is running again. And now 12.5 for append day is running, and 12.4 for report is running because the report can now be sent. And if you keep waiting, we will see that the report for 12.5 for append day is finishing, and the 12.5 for report is also running. Okay, we'll look at one more command for the safe QA or experimentation. Let's say I want to try a different version of this report with only 2 days instead of 20 days or 30 days. How do I do that? So I have the code for this committed in a branch called demo append day 2 day. And so how this is how I run this version, this variation. So execute append day 12.5, wait, and take the code from a branch, and output the results to a different label. So we have the label and the branch to be the same. And when we run this, let's take a look. Okay, so that ran through. If you look here, it says that the branch is demo append day to day. The inputs are from prod, but the output label is demo append day to day. And if you look at the data sets, we'll see both of them exist at the same time. Two different 12 fives with two different labels. If you look at it more detail, if you open this one and this one, then the first one should have 4 days of data, and the second one should have 2 days of data. So this is the first one, it has 4 days of data, 12.2, 12.5, 12.4, 12.3, and this should have only 12.5 and 12.4. All right, so this is the end of the demo. As you can see, catalog-based dependency builds a pipeline with predictable and safe data transformations, and Trell makes it easy to build and maintain such data pipelines. If you like this video and think catalog-based dependency is promising, please like, share, and retweet this video. That would help a lot to get the word out. Thank you for listening.